welcome back. We're going to head into our last section in Chapter 4 that we're going to go over. It is on Section 4.4, which brings in some exponential and logarithmic equations. So we alluded to some of these exponential ones in Section 4.2, but we'll actually get some that we'll be able to solve, and then we'll head in to do some logarithmic equations as well. So let's look at our exponential equations. An exponential equation is an equation containing a variable in the exponent. That shouldn't be very hard to kind of decipher. And it would be something that looks like this. Maybe 2 to the 3x minus 8 equals 16. Maybe I have 4 to the x equals 15. And maybe I do something like 40e to the 60th x or something like that equals 240. Okay, so those are all examples of exponential equations. Notice that the variable is in the exponent. Now, there are two basic steps in order to solve an exponential equation. Basically, we want to write the equation of the form b to the m equals b to the n, where we basically have the same base on both sides and one exponent. So we're going to use our law of exponents in order to get condensed down to all of that. And then we are going to set m equal to n, which are your exponents. The bases are the same, therefore the exponents have to be the same, and that's where the variable is. So we're going to just set each one of those equal to each other and solve, okay? So, sounds easy. Let's try it and practice it. If we look at here, 5 to the 3x minus 6 equals 125. Then what we want to make sure, again, is that we bring it down to one base with an exponent on each side. Well, we have that on the left side. Problem is, on the right side, we don't have the same base, so that becomes the question. Can I write 125 as a base of 5? And the answer is yes. 5 times 5 times 5 is 125, so I could condense that down to 5 to the third power. So I have the same base on each side, therefore the exponents have to be equal. If those bases are equal, therefore, that's, whoops, the 3 dots, not the one in the middle there, let me undo that. The 3 dots in math like that means therefore 3x minus 6 would have to equal 3. And this is a nice two-step equation that I can solve by adding 6 over to the other side to get a 9, then dividing by 3 both sides to get a 3. Therefore, solving that equation, the x value is equal to 3. Okay? Now, on the second equation, I already have a base to a power on each side, but unfortunately, the bases this time are not the same. And unfortunately, if I look at the smaller one, can I take 4 to a power to get 8 would be the question that I have. And actually the answer is no, I can't. So that's the easier of the version. If you can take one or the smaller base and make it as a power of the other, then you only have to work with one side. But unfortunately here, I have to do both. So we would have to find the common base. If I write 4 as a power, then that would be 2 to the second power. Well, then the question becomes, can I take 2 to a power to get 8? And the answer is yes. So let's work on the right side. I'm going to create that 2 squared for that 4. But remember, that's still to the x minus 3. Then our 8 can be written as 2 cubed to the x plus 2 power. And so now what I need to do is do my law of exponents in order to get our base to 1 power, because now we have a base to 2 powers. Well, by our law of exponents, this is the property where I have to multiply both of those together. Well, if I have a 3, then I remember I have to multiply by both of those. So the left side becomes to the 3x plus 6, 2 to the 3x plus 6. And the right side, when I distribute that 2, becomes 2 to the 2x minus 6. And now I have bases that are the same. I now need to set the exponents equal to each other. 3x plus 6 has to equal that 2x minus 6, and now solve that equation for x. So when I do that, I subtract that over. I'm going to subtract 2x from both sides. I'm going to subtract 6 from both sides. These two are going to cancel, and I'm left with an x, and I'm left with a negative 12. Therefore, to solve this equation, x would have to be equal to negative 12 in order for that to be true. Okay? All right, very good. So that's how we work with exponential equations. Now let's turn our attention to logarithmic equations. There are times when you cannot get the same base on both sides in order to solve. In this case, we will need to use logarithms to solve the exponential equation. So we're going to first isolate our exponential expression. Number 2, we're going to take the common log of both sides of the equation for base 10, and we're going to take the natural log of both sides of the equation for bases other than 10. Now, I will tell you that it doesn't matter. You can take the log or the natural log of either side. It doesn't matter with that. You can do either or, okay? So, you'll get the same answer in the end. So, when we simplify, after we take the log of both sides, we have to remember a couple properties. We have to remember that natural log of b to the x is going to equal, when I bring that x out front, x times the natural log of b, okay, where I have a power, and do the product of that. I also want to make sure I remind myself that the natural log of e to the x, since the base is e here, e to what power is e to the x? It is equal to x. And if I have the log of base 10 to the x, okay, log of base 10 of 10 to the x, 10 is the invisible base here, 10 to what power is 10 to the x? It is equal to x. So some of these properties we want to make sure that we remember. You know, it does get kind of tricky sometimes, so you have to check things out, okay, and watch. So here we have a base that is other than 10. So technically what we want to do is to take the natural log of both sides. So in order to simplify or symbolize that, I end up doing this, okay? Now, I will tell you that if you take the log of both sides, in the end, your answer will be the same. But for our purposes, we're going to stick with kind of what our notes say here at this point. All right, so if I have natural log of 5 to the x, this base is in e. Well, e to what power is 5 to the x? Who knows? So what I'm going to make use of is this guy right here, because I want to solve for x. I want to get x by itself, because in this original equation, I could not easily write 134 as a base of 5. So that's why I couldn't solve it like I did before. So, natural log of both sides, I'm going to take this power and bring it out front. And that was our third law that we saw in section 4.3. So I bring x out, multiply it by the natural log of 5, and set it equal to the natural log of this 134. Now remember, this is just a product. And remember, this is just a number. Type it in your calculator. You'll get a nasty decimal. It is just a number. So if I have a number multiplied by a letter, I can divide by that number next to the letter in order to get my answer, because this goes to 1. No matter what the number is, if that's the same on top and bottom, you go to 1. Therefore, x equals the natural log of 134 divided by the natural log of 5. And that right there is something you could put in your calculator and figure out the answer for. Now, as a decimal, this is the exact answer. Now, if you did the log of both sides, then you would have the log of 134 over the log of 5. That would be another possible answer, okay? Now, here I have a base of 10. When I come up here, we're going to have isolated the exponential. We want to take the logarithm of both sides for base 10. So this one, by our notes, tells me I do definitely need to take the log of both sides. And I'm going to make use of this property right here, where I have an invisible base 10 to what power is 10 to the x? Well, it is the power of x. That's what I'm looking for by that property. We can condense all this down just to x is equal to the log of 8,000. Again, you can put that in your calculator for a decimal value, but this is the exact answer, okay? Now, our third problem does not have our exponential isolated by itself. So that's where I'm going to add 5 to both sides. We did this with some absolute value equations, but this becomes 63. Then I can divide by 7 both sides. That's very nice. Get rid of that. So I have e to the 2x is equal to 9. Now, the base that I have there is something other than a base 10, so we're going to take the natural log of both sides. Again, I can't get 9 as a power of e, So I have to do this process to solve exponentials using logs. So we're going to take the natural exponential of both sides. And I'm going to make use of this property right here. Our invisible base is e. E to what power is e to the 2x? Well, 2x is the power. So that's what that comes down to be, equals the natural log of 9. And then I can solve nicely for x by dividing both sides by 2, claiming that x now is the natural log of 9, divide by 2. And that would be our final answer for that equation. Okay, so two ways to solve exponential equations. One where you can easily get the same base, like these up here. The other where you cannot get the same base and you have to do the log of both sides. These are a little bit more difficult than the ones, just because you haven't really seen that before as much. Okay? All right, let's turn our attention to logarithmic equations. And there's going to be kind of two types that we see of this. And so a logarithmic equation is an equation containing a variable in the logarithmic expression. So some examples of logarithmic equations could be log base 4 of x plus 3 equals 2. We may have also like the natural log of x plus 2 minus the natural log of 4x plus 3 is equal to the natural log of 1 over x. So they kind of get a little bit big sometimes. But by using our law of logs, our log properties, we could actually condense that down to a division from section 4.3. So here's some basic steps to use in order to solve these logarithmic equations. We want to rewrite the equation in the form of log base b of m equals c. Log base b of m equals c. Then what we want to do is we're going to rewrite that equation in its corresponding exponential form. If I can spell. Okay. Then we're going to solve for the variable, just like what we were doing prior, and then we are going to check the proposed solution. This is important for these logarithmic functions because if you recall when we were working with the definition of logs, this base and this expression, well, this had to not be equal to 0, but this expression m had to be greater than 0. So we have to guarantee that whatever variable I get, for every expression that I see, that I would get something that is positive and not equal to 0. Okay, so let's try a couple of these here on this one. So here I have, rewrite the equation into that form, which I have, log base b of m equals c. Then we're going to do the corresponding exponential form, which if you recall, we took this base to that power equals this. So we would have 2 to the third equals x minus 4. And then we have to solve it. This one's not too bad. This gives me an 8 equals an x minus 4. And when I add 4 to both sides, this gives a 12 is equal to x. So this I'm circling, but we have to double check that when I plug 12 into the original, that the expression that I get here is positive. So 12 in there minus 4 is 8. We are good. Okay? Now, let's try to solve this logarithmic equation, and it's a natural log. Notice I don't have exactly of this form because I have a 4 hanging out. Well, that's 4 times that natural log. So if it's multiplied, let's do ourselves a favor and divide both sides by that number. So I get the natural log of 3x is equal to 2. And then let's write our corresponding exponential. Now remember, this is a base of e. So the natural exponential e to the second power is equal to this expression here, which is 3x. And then I'm out to solve for x. Okay, we got to get x by itself. Well, it's 3 times x, so I'm going to divide by the number next to the letter. Therefore, x is equal to e squared all over 3. That is the exact version. If they were to request you to do a decimal value, you can just plug that into your calculator and find out what the decimal value is. Now, when you put this into here, remember the natural exponential is like 2.718 or something like that. When you plug that into here and times it by 3, the 3's are going to cancel, leaving you with e squared. So it's going to be positive. Therefore, that is a valid answer right there. Okay? All right, and our last one on the front side here of this page, gives us a little exercise in getting it to here using our law of logs, okay, or the properties of logarithms. So notice I have a product of two logs. So when I did the exercises of taking multiple logs down into a single log, that's why we did it, okay, to practice that. Because the sum of two logs is actually the product of a single log. So I have the product of x and an x minus 3 equals that one, okay? All right, very good. Now we have our log base 10, which is invisible, of m equals to c. So we're going to take it and write it in its exponential form. Let's go 10 to the first equals this x times an x minus 3. Now in order to solve that, I'm going to have to distribute those that x through those two terms. So I'm going to write this as x squared minus a 3x. Now, that is a quadratic equation that I'm going to have to solve because I have a square there. So I'm going to subtract over the 10, but also kind of flip-flop sides. So I get x squared minus 3x minus 10 equals 0. And I can now factor this. It's a trinomial, nothing in common, but it is one that I can make my x and my x. Last sign is a minus, so they are different, so a plus and a minus. 1 in front tells me I can say, what do I multiply to get 10 that I subtract to get 3? And the answer is 5 times 2 gives me 10. 5 minus 2 is 3. Now I need a negative 3, so I need a minus 5 and a plus 2 there, okay, to get the minus 3. So what makes this 0 is negative 2. What makes this 0 is a positive 5. Now, we have to make sure that both of these answers will create positive expressions out of there. So when I have a negative 2 in here, that becomes negative. There's no way that can be an answer. If I put 5 in here, that's positive. If I put 5 in here, minus 3 is positive. Therefore, x equals 5 as my final answer there. Okay? All right. Very, very good. These sections go pretty quick, actually. Okay, as long as you kind of get the hang of it. And so, our last 3 problems that we have for section 4.4 is how did I solve a logarithmic equation with one-to-one property? So instead of writing it as an exponential, where I have a log on one side, now these equations are going to be to where I have logs on both sides. So we want to write the equation to where I get it into the condensed form of log base b of m equals log base b of n. So now I have a single log on each side. And we want to set the logarithmic expression equal to each other. Well, this is equal and this is equal, therefore m must equal n. That's what I mean by that. Then we're going to solve for that variable, and now we want to make sure, again, that we check those proposed solutions so that m is positive and n is positive. So both of those expressions must be positive, okay? All right, very good. So let's try this. First example, I do not have that form because I have a number out front. So what I want to do is I want to bring that number by our power rule of logs. I want to bring that in as an exponent. So that would be log of base 10, which is invisible, of x to the third is equal to log of 125. So now I have this expression. I have a single log on the left, a single log on the right. Therefore, I'm going to set each one of those expressions equal to each other. Therefore, x cubed has to equal 125. Now, you may know what this is. What do I cube to get 125? Or you can undo this by cube rooting both sides. And this, that cube cancels that cube root, leaves me an x. And the cube root of 125 does become 5. And I circled that without checking, but make sure when you plug that in, that does become positive. There's no variable to put in over here, so you just have to put it in one side for that problem. Okay? X equaling 5 is our answer. Now, the next one, again, I don't have a single log on the left side. I do on the right side, but I don't on the left. Now, it's the difference of two logs can condense down to, if you recall, that's law 2 of our logs, or property 2, of the quotient of a single log. So I have to take this x plus 7 and divide by the 3, set that equal to my 7x plus 1, and now I do have this form. I have a single log on the left, a single log on the right, same basis. Therefore, I can set this expression equal to that expression. Therefore, x plus 7 all over 3 has to equal 7x plus 1. Now, we have an equation that we can solve. Actually, it's not too bad. I'm first going to get rid of that fraction. If that's a divide by 3, let's multiply by 3, which means I have to multiply all of this by 3. So I'm left with what's on top, which is x plus 7. And after I distribute, I get a 21x plus 3. And I'm going to do this. I'm going to minus x and minus x, so I have a 20x here, which means I have to subtract 3 and subtract 3. So this goes away, that goes away. This leaves me with a 4 is equal to a 20x. When I divide by 20, I can't reduce by 4. Therefore, x here becomes a 1/5. Now again, remember, we have to check our expressions. If I put 1/5 back in here and add 7, do I get something greater than 0? The answer is yes. If I multiply 7 times a fifth, that gives me 7/5. And when I add 1 to it, I'm still not going to equal 0. Therefore, x equaling 1/5 would be my answer. Okay? All right. Very good. Last question that we have. Again, it looks very similar to this one, but actually it combines kind of this guy also. Because I have this 2 in front, I'm going to bring it in as a power. So I would get log of x squared minus log of 7 equals log of 112. So I still need a single log on the left side. Well, the difference of two logs can be condensed down into the single log as the quotient of those expressions. Set that equal to log of 112. And now I have a log on the left, a log on the right. That means I need to now set the expressions equal. So therefore, x squared over 7 has to equal 112. Now, to solve for x squared, I'm going to times by 7 both sides. And when I do that, 112 times 7 gives us a value of 784. Now, just like what we did over here, we cube rooted both sides. Over here, I have to square root both sides. But when we square root both sides, unlike the cube root, remember, there are two answers that kick out. Now, 784 is actually a perfect square. Okay, if you put it in your calculator, it's probably not one that you remember. Plus or minus 28 would be the answer. But remember, we have to make sure that the expressions are positive. And so this is my only expression right here with the next. I need to just choose the positive one, not the negative one. So therefore, x has to equal 28 here. That's the only answer that works. The negative will not. Okay? All right, very good. So there's basically kind of 4 different sections here on how to solve 4 different types of equations. And they're not too bad once you kind of get them and use those properties. Get them into the form that they need, set the powers or the logarithmic expressions equal to each other, and solve. Don't forget to check your expressions on these logarithmic equations because it does make a difference. So, until next time.